Okay.
Good morning.
The first thing, please tell me, do you see the white sheet on your screen?
Yes. Yes.
Yes.
All right. Okay. So welcome everybody for today's classes from electronics. And please tell me, do you prepare some coffee? Because I ask you because I think today I think the coffee could help you because we will starting with the Laplace transform, and we'll have a little bit math today. Yeah. So okay, let's starting. Great. As I know, you had some Laplace transform some information about the Laplace transformations on the lecture, I think. Yes, that's right. Yeah, Jakub?
Yes.
All right, thank you, Grzegorz. All right, so before we're going to electronic circuits and solving some problems with it using the Laplace transform, we have to know how we can make some transformation between the functions from the time domain to the Laplace domain and opposite. Why it is so important? This math it is necessary for the future electronic circuits, solving some electronic circuits based on this this transformation. All right. So theoretically, everything about the Laplace transform you know from the lecture. However, today I'm just wanting to show you how we can use it in practice, making some examples. Okay, one thing again. Today we've got 2 hours. Yeah, we have two hours of the classes. All right, great. So first of all, I'm just wanting to show you step by step how we can find the Laplace transformation function from time domain function. If we have the time domain function, we can calculating. You can find the Laplace transform of it. Great. So first example. Find the Laplace transform from ft function if ft is equal, okay? And the first function in the time domain looks like that. A plus a squared t plus a e power to minus et plus a squared times cosine function from at. Of course, the a, this is the constant value. This is some number. Okay, this is our some function in time domain, and we have to find the Laplace transform for this function. So we have to go from time to the Laplace domain. Great. First thing, you can see here that we have the summing of few math components in time domain. A squared t, a power to e to minus et, and the a squared times cosine omega t. So the first properties of Laplace transformation is that if we have the function which is equal to the summing of some components, the Laplace transform of the total function, it is equal to the sum of the Laplace transformation of each components. Yeah. So so the Laplace transform from the ft will be equal to Laplace transformation from each component of the ft function. So this is Laplace transform from a plus the Laplace transform from the a squared t plus Laplace transformation from a e to minus et plus the Laplace transformation from a squared times cosine et. Yeah. Okay. So let's counting this component. This is the first one, the second, third, and fourth. Okay. Okay. So please tell me, do you had on the lecture some tables or table with the Laplace transform functions? Yeah or not?
Bo cię mam jebnąć znowu i znowu się ma oprzeć sprawa o policję. No i dlaczego, że masz wykład? To nie możesz się odezwać? Nie możesz powiedzieć, przepraszam tato, bo jestem zajęty. Mam wykład. Nie możesz się do mnie odezwać?
Czy słyszycie tutaj kogoś?
Powiedz chociaż słowo jedno. Przepraszam, nie mogę. To później zrobimy. A ty się nic nie odzywasz.
Hi guys. Do you hear these voices?
Yeah.
What do you think about it?
I think there will be no more because he muted. So
Okay, never mind. Great. So please tell me, do you have some this table with the Laplace transformation?
Yeah, there was a slide with this.
Yeah, of course. So as you see, it is necessary to have it because we'll use it from this moment. We'll use it very often, and the first thing, you don't have to, in fact, learning the whole of the table. Why? Of course, you have to know this typical Laplace transformation function. If you make some practice, in fact, you remember it. However, on the tests, in fact, you can have with you this table. So as you see, you can use it also on the tests. Okay, that's the first thing. All right. So let's coming back to our example. The first function, the first Laplace transformation, it is the Laplace transform from the constant value. That's right. Of course, this is the function e. It is in time domain. Yeah. So how we can express it? In fact, a. This is the constant. So constant. First thing, the constant, it is coming, can be moved before the Laplace transformation. And what you've got here? Here we've got the unity function inside. In fact, if you have the function in time domain equal constant value, like a, in fact, this is the a times unity function. Oh, unit function. 1t. Why? Because we have to we can express it in that form that it is the function in time domain. Okay, so in fact we've got the Laplace transform from unity function. how many it is? The Laplace transform from the unity function, if you take a look on the table, you will see it is equal 1 over s. So this is 1 over s times the constant value, a. Okay? So this is the a over s. Okay. The second component. This is the Laplace transform from the a squared t. So in fact, a squared, it is constant value. It is coming before the Laplace transform function. And we've got the Laplace transformation from t. Okay, and again, you can go to the table and you'll see that the Laplace transform from t, it is equal 1 over s squared. Yeah, and we have to adding the a squared here. Yeah, so as you see, we've got a squared over s squared. Okay. Next thing, the next component, it is e times Laplace transform from the e power to minus et function. Okay, and again, if you take a look on the table, you will see that the Laplace transform from the exponential function power to minus et, where a, it is also the constant, it is equal anytime 1 over s plus a, where a here, it is the constant value. And what you have to know, this original function, it is e power to minus et. For this function, where we have the minus here, the Laplace transform, it is equal 1 over s plus e. So you have to remember, if we have the minus here, here we've got the plus. If I will have the function Laplace transformation from e power to et, it is positive power, the power part is positive, then I will have the Laplace transformation equal 1 over s minus a. Okay, so we have to remember it. So please write here some notes. The Laplace transform from the e to at, in fact, this is 1 over s minus a. Okay, great. And again, I have the constant value, which was previously moved outside the Laplace transformation function. So as you see, I've got the e over the s plus e. And the last one, it is the Laplace transform from e squared times cosine et. Okay, and again, this is a squared, it is going before the Laplace transform, and I have cosine et function. All right, so so we have to find what is the Laplace transformation from cosine et function. In fact, I can show you this table. I can find, I found it on the internet, of course. Where it is, here it is. Yeah. This is the table of the Laplace transformation, Laplace transform functions, and we can see here what is, for example, here it is, the Laplace transform from the t function. It is here, the unity function ut, it is 1 over s, as you see. What else? Oh, here it is. E power to minus alpha t, it is 1 over s plus alpha. Yeah? So as you see, we can use it, in fact, anytime. What else? We've got the cosine et. Here, it is the cosine omega t times unity function, of course. I've got the cosine omega t. In our case, omega, it is a. So as you see, it is the s over s squared plus omega squared. In our case, it is the omega, it is a. So in my case, it will be equal a squared, and the Laplace transform from the cosine, as you know, it is the s over s squared plus, there was the omega, we've got the constant, not omega, but a, plus a squared. Okay, so finally, we've got the a squared times s over s squared plus a squared. All right, so now, if you got the Laplace transformation for each component, so the total Laplace transform from the t function will be equal sum of the Laplace transform for each component. So the first one was a over s plus a squared over s squared plus, third one, it is a over s plus a, and the last one, it is a squared times s over s squared plus a squared. As you see, this is the Laplace transform function from ft function. Okay, so that's the way how we can go from the time domain to the Laplace domain. Okay, great. This is the first example. As you see, I choose especially that example because we used the three different function to make the practice with the Laplace transformation, Laplace transform calculations. Great. The next example will be a little bit difficult. Yeah. And our function in time domain is given by that expression. It is e power to minus et times, for example, sine omega t times, of course, the unity function. However, unity function, it is t minus 1. What does it mean? Maybe you remember from the classes what was previously when I talked about the unity functions or the gate function. Yeah? The t minus 1, it means this is the unity function which is shifted by 1. In this case, if the time is in seconds, it means this is the 1 second. So the unity function is shifted by 1 second to the right. Yeah? So our function, in fact, is starting from the 1 second, not from the 0 time, but from the 1 second. All right. So how we can solve it? The first thing, we haven't the unity function equal t, but it is shifted. It is shifted. So let's go to our table with the Laplace transformations. Maybe it is here. No, I can see it. No, this is not here. And maybe, okay, here it is or not? Here it is. No, I haven't it this moment. No, I haven't it in this one. You have it on your your table from the lecture. Okay. So I'm just tell you how we can solve it. Okay. Typically, if we have the function which is where we have the unity function which is shifted by some value, the Laplace transform we can found from such general equation. If ft function it is multiplied by unity function which is shifted by some t0 time, then Laplace transformation from that function it is equal e powered to minus t0s times the Laplace transform from our function in time domain. However, the time by time we have to substitute t minus t0. This is the general expression where we have the unity function shifted by some value. Okay, so let's take a look at our function. Here we've got this part of the unity function t times t minus t0. In our case, it is the u t minus 1. Okay, as you see, t0 it is 1 in our case. Everything what is here, this is our function. In fact, of course, this is the coincidence of the function. So let's call this part of our function like the gt function. Okay, and then we can write that the gt function times unity function t minus 1, in fact, using the Laplace transform, we have what? According to the general expression, e powered to minus t0s. In our case, as you see, t0 here, it is 1. So it is minus 1 times s. So this is the minus s. I don't have to put it here, the 1, of course. Great. Times the Laplace transform from g function, however, not from the t, but t minus 1. T minus t0. So t minus 1 in our case. Great. So as you see, e powered to minus s, we've got it. So everything what we have to do here, so we have to find the Laplace transform from our gt function, but by the time we have to substitute t minus 1. Okay, let's do it. How many it is the g from t minus 1? Okay, so this is equal e powered to minus e by t, we have to substitute t minus 1, okay, times sine omega t minus 1. Okay, that's all. Okay, great. So this is equal. Look, let's multiply the e by the components in the bracket. So this is the minus e t plus e, because this is the exponential function. If we have, in the power, if we have the summing or summing up of some components, in fact, this is the same like the multiplication of the exponential function powered to each component which is exists in the power place. So in fact, it will be the e powered to minus e t times e, and the second component plus e. Yeah, a times 1, it is a, minus and minus gave us the plus, so this is the This is the A. That's right. One thing here. Okay. I think that I make some mistake here. Okay, this is the mistake. If we got the minus here, so here we have to put the plus. This is my mistake. Sorry. So, so here we have to put the plus. Yeah, that's right. So we have to put it here, the pluses. Sorry for that. Great. So it will be the minus ET minus E. Okay, so this is the minus E times the sine function from, if we multiply the omega by the brackets, we'll have the omega t plus omega. Great. So this is our function g from the t minus 1. According to the, we have to find the function here. We have to find the Laplace transform from this function. In fact, where the f it is g, and we have to substitute by the t plus t0. Sorry, plus t0. All right.
Sorry.
Yeah.
Argument of g is t minus 1 or t plus 1?
Sorry. Here we have to put the plus. Yeah.
Okay.
Thank you, Jakob. All right. So the Laplace transform from our the ft function totally will be equal. We have to coming back, and this is our ft. We have to coming back to this one, and as you see, according to the general expression, the Laplace transform from this function, which is in fact here, it is equal e power to minus s. Yeah, that's right. Okay. Times Laplace transform from this one, e power to minus et times e to minus e sine omega t plus omega. Okay, great. First thing, we have to take a look where we have the constant values, where the functions or the components without the t, in fact. Yeah? This is it. Yeah? So the e can be moved before the Laplace transformation function. Okay, so it will be equal e to minus s times e to minus a. Yeah. Okay, how many it is? It is the e power to minus s plus a. That's right. This is the same like the e power to s times e power to minus a. All right. So times, and the Laplace transform from e to minus et times sine omega t plus omega. So this is equal e to power 2 minus s plus a times. What you can do here, look, we know what is the Laplace transform from the sine function and cosine function. So we have to go and to remember, you have to remember yourself the properties, in fact, of the geometrical functions, or like the relationship between the cosine and the sine function, where we have, for example, sine at plus b. Yeah, how many it is? In fact, we've got some properties of the sine function which tell us that this part of the expression can be given by that formula. This is the same like the sine omega t times cosine b, where b it is the omega, plus cosine omega t times sine from the b. In fact, this is the omega. Okay. So, in fact, this is the same expression like this one. Okay. So, let's take a look what we've got. We've got the multiplications. Everything is multiplied by e power to minus at. However, inside we've got the plus. So, if we have in fact, we've got the two components, in fact, yeah, the summing of the two components. So the Laplace transform from this total expressions, in fact, will be equal to the sum of the Laplace transform from this part and this part multiplied by e power to minus at. Okay, so it will be equal e to minus s plus a, okay, times what we can do. Look, if you multiply this part of the expressions by e to minus at, we'll have this function times sine omega t multiplied by cosine omega. Cosine omega, in fact, this is the constant value. Yeah? The omega is constant. So it can be going before the Laplace transform function. So we've got the cosine the omega times the Laplace from e power to minus at times sine omega t plus, and again, e power to minus at times cosine omega t times sine omega, in fact, and the Laplace transform from it is the same. However, in this case, the constant value, it is sine omega. So sine omega is going before the Laplace transform function, and this is equal e power to minus at times cosine omega t. Okay, so we've got it. Why this table is so important? Because look what we've got. This is the constant values. But here we've got the Laplace transform from that expressions, e power to minus at. We know how many it is. The sine, we know how many it is, the Laplace transform function from it, and also from the cosine. However, please take a look on the table. Do you see it? We've got the e power to et, yeah, sine bt. Yeah. You've got it? Do you see it?
Yes.
All right. So as you see, for the sine function multiplied by e to at function, in fact, this is the same. This is the same function like for the sine function. It is like the Laplace transform from the sine function. However, by the s, we have to substitute the values which is from the function like the e power to et. Do you see it? So if we have okay, I'm just we can note it in fact here. Okay, from the table we've got e power to at sine bt. After Laplace transformation, it is db over s minus a squared plus b squared, and the e power to at times cosine bt. This is the same like the s minus a over s minus a squared plus b squared. Okay, I'm just switching the screen to desk to the dashboard. I'm just redraw this expression from the table. Why? Because I just wanted to show you that in fact we've got the we know how many it is, the Laplace transform from these expressions. Why? Look, here we've got the e power to at, we've got the e power to minus at. Okay, so where's the differences? I told you before. If you have the minus at, in fact, Laplace transform from this function is 1 over s plus a. Yeah. If we have the minus here, the Laplace transform from this function separately will be 1 over s minus a. Look, s minus a. If I will put it here, the minus, in fact, here it will be the s plus a. Okay, this is the one thing. Times sine bt. Look, this is the b is going here over. This is the s squared for the sine function, separated sine function. However, we've got the e power to at. So by s, in fact, we have to substitute the s, in this case, minus a. In our case, it will be the s plus a because we've got the minus here. What is for the cosine function? Without it, the Laplace transform from the pure cosine function will be equal s over s squared plus b squared. With this function, everything is the same. However, by the s, we have to substitute the s, in this case, minus a. That's all. Okay? If you have the e power to minus at, so we'll have the s plus a and s plus a and squared. Okay? So, why I told you in that way? Because you don't have to remember so huge theory, in fact. It will be much more faster to understand it and solve the problems. Look, so let's coming back to our example. So it is equal e power to minus s plus a, one thing, times, okay, the cosine omega, it is constant, times Laplace transform from this function, it is equal. This is the sine function. Please take a look at. Look, it is the b. In our case, the b, it is the omega. Yeah, that's right. So we'll have the omega over s plus a squared plus omega squared. Omega over s plus a squared plus omega squared. Right. Plus sine omega times, and the Laplace transform from the cosine function, it is equal s, in our case, it is not the it will be the plus a because we've got the minus here, over s plus a squared plus b. In fact, the b, it is the omega. Okay, that's all. As you see, step by step, we solved the problems and we found the representation, this function in the time domain. We found the representation in the Laplace domain, which is presented here. This is our Laplace transform from the ft function. Okay. Okay. I showed you how looks like the transformation with the shifted unity function. So as you see, it is much more harder. Great. The next things, the next example. Okay. Okay. And the ft function, it is equal 1 over 2 t minus 4e power to minus 2t. Of course, times unity function. Of course. Okay, so first thing, let's multiply it everything by the constant value. So it will be equal t over 2 minus 4 over 2, it is 2 e power to minus 2t. Great. So if you wanted to find the Laplace transform from our ft function, as you see, we have to subtract two components. So in fact, the Laplace transform will be the subtraction of the two Laplace transform from each component. So it is the Laplace transform from the t over 2 minus Laplace transform from the 2e power to minus 2t. Okay. So it is not so hard, yeah. We've got the 1 over 2, it is the constant value, so it is going before the Laplace transform function, minus, and 2 is going before it also. Oh, sorry, it is 2t. And this is equal 1 over 2 times, what is the Laplace transform from the t? We have to go to the table or the first example. How many it is? Please take a look. What is Laplace transform from the t function?
One over s?
No. From the t function, not from unity function. The first example. Yeah. This, the second component with the first example. So not with, but in.
1 over t squared?
No. Laplace transform from
1 over s squared.
That's right, of course. Yes, of course. Yeah, this is it. Minus 2 times. Here we've got the Laplace transform from the e power to minus 2t. As you see, a, the constant a, it is here, it is the 2. Yeah. So how many it is? The Laplace transform from the exponential function power to minus t.
1 over s plus 2.
Yes, excellent. 1 over s plus 2, where 2, in fact, this is the a, yeah? This is the constant a here. Yeah, as you see. Great. So, in fact, this is equal 1 over 2s squared minus 2 over s plus 2. Great. Okay. What else? maybe we can make another example with this unity function which is shifted, because I think we have to make much more practice with it. Let's say we've got the function in time domain equal t e to minus t minus 1, okay, times unity function, it is shifted by 1 seconds, minus e powered to minus t minus 1, of course, multiplied by t minus 1. All right. So, what do you think? How we can starting here, or how we can starting with this example? What you will do firstly, if you see that example, what are you going to do?
Factor out the u times u of t minus 1.
Yeah. So yeah, great idea. So it will be the t to e minus t minus 1 minus e to minus t minus 1 times unity function shifted by 1. Yeah? That's right?
Yes.
Yes.
Yeah, great. So, in fact, we've got again the same situation. This, for us, let's say this is our GT function, for example, times unity function shifted by 1. Okay? So, as we remember, GT function times unity function shifted by 1, the Laplace transform from such a function, in fact, it is equal in general, yeah, as you remember, e powered to minus t0s times Laplace transform from the GT function, however, calculating for not the t, but t plus t0. Yes? Yeah, all right. So, what do we have to do? Laplace transform from the total ft function will be equal this expression. So this is equal e powered to minus t0s. In our case, here we've got, this is our t0. Yeah. So how many it is? It is 1. It is 1. So it is e powered to minus 1 times s. So it is e to minus s times the Laplace transform from GT function, where the t is substituted by the t plus t0, so it is equal. So let's substitute it. This is our GT function. So let's substitute by t plus 1. So it is t plus 1 times e powered to minus, and here we have to substitute by t plus 1 and minus 1. Okay. Okay. Minus. Here it is the e powered to minus t plus 1 minus 1. Okay. Got it? So this is equal e powered to minus s times Laplace transform from the t plus 1 times e powered to minus t minus e powered to minus t again. Okay, great. So this is equal e powered to minus s times the Laplace transform from, let's multiply the e power to minus t by this bracket, t plus 1. Yeah? So it will be equal t times e to minus t plus e to minus t times 1, this is it, minus e to minus t. So as you see, we've got a situation where this component is reduced with it. Yeah, this is the plus and this is minus. Yeah. So finally, we've got the e power to minus s and the Laplace transform from the t e minus t. Okay. Great. How many it is?
1 divided by s plus a squared.
Yeah, that's right. That's right. Dominic, yes?
Yes.
It was not great, Dominic. Of course. Do you found it on the table?
Yeah.
Great, great. So this is equal 1 over s plus 1. In fact, yeah, because here the a, it is hidden here. Yeah, it is 1. A, it is 1 here. Yeah? In this case, it is 1. So as you see, this is e to minus s plus 1 squared. That's all. Great. What else? We can make it the last example very, very fast. Let's say we've got the function in time domain equal e to minus 4t, t minus e minus t. Okay, something like that. So what do we have to do firstly? Let's multiply this component e to power to minus 4t by the bracket. So yeah, so this is the t, e minus 4t minus, how many it is? E. As you see, we've got the minus here, minus here. We have to substitute the power values. So it is the minus 4t minus t. This is the same. So this is equal t to times e to minus 4t minus, how many it is? E power to how many it is?
Negative 5t.
Yeah, minus 5t. Yeah, of course. Great. So the Laplace transform from the ft function will be equal. The Laplace transform from the t e minus 4t, it will be equal, how many? As previously, t powered to e to minus t. In fact, in our case, this is the t powered to t times e powered to minus 4. A, it is a factor, it is 4. Yeah. The constant, it is 4. So it will be equal 1 over s, this is the minus, so the plus a squared. A, it is 4. Okay. And minus, and the Laplace transform from it, it is simple. It is 1 over s, this is minus, so plus a. A, it is 5. That's all. This is it. Great. So as you see, we've got we made some examples which tell us how we can found the Laplace transform function, or how we can going to the Laplace domain, having the function in time domain. Great. So now let's try to make some opposite example. We've got the Laplace function. Yeah, we have the function Laplace domain, and we have to find the function in time domain. Yeah, so this is the opposite way. Great. Do you have it on the lecture or not? Such conversions between the domains, from the Laplace to time and time to the Laplace, or not?
It was mentioned, but it was pretty fast, so.
Okay, I see. So, but please tell me, do you feel it? In fact, how we can find the Laplace domain function, basing on this examples, what we done? The silence.
Well, I think we need to practice more, but
Of course,
I think it's clear.
Thank you. Great. Okay, I have to take papers. All right. So if you wanted to start to talking about the opposite transformation from the Laplace to the time domain, here we have to remember some part of the algebra math properties, in fact. Maybe I told you, maybe I show you on the examples. I think this is the best way. However, if you wanted to find the ft function for given function in S domain, in fact, we can have three different, in fact, types of expressions. It is called like the simple. This is the expressions with the simple poles. Simple poles example. We have the multi-poles example and the conjugate pole examples. And now, I just want to show you how it looks like the transformation for each type of functions. For example, first one. Let's say that for given fs function, find ft function. Yeah, it's very simple. Okay, so the first function is in the S domain, so in the Laplace domain, it is equal s plus 1 over s plus 2 over times s plus 6. Okay, so this is our function, yeah, in S domain, and we have to find this function in time domain. However, as you take a look at on the denominator, we've got the two components which has some roots. Yeah, what is the root for the first component, s plus 2? Do you know how many it is? Minus 2, yeah? That's right. For the second, the root it is s plus 6. Where, in fact, when this example, this component is equal to 0, when the s is equal to minus 6, yeah? So this is the root for it. And from the math, and from the algebra, maybe you know how we can express the same function using the poles. We can express it. How? We know where's the roots here for this component and this one. So everything can be expressed like that. The key one factor over the first component s plus 2 plus k2, this is some coefficient here, s plus 6. Yeah. So as you see, this case where we have just simple components like the s plus 2, s plus something, it is the example for simple poles example. And if you wanted to express the fs function in that way, firstly we have to find the factors key1 and key2. How we can make it? Very simple. And our fs function, it is equal. Let's calculating the key1. Okay, for key1, as you see, the first component, the components connected with the key1, it is s plus 2. So for the root of this component equal minus 2, yeah, for s equal minus 2, we know that this component is 0. Yeah, that's right, it's reduced. So what we have to do here, our fs function, it is equal this function without this component, in fact, when we're calculating the key1. Okay, so it will be equal s plus 1 over, and here we have to remove the expression, remove the components which is connected with the key1 factor. So it stays s plus 6. And everything is calculating for the s equal minus 2. Minus 2, it is the root of this component. So it is equal, how many? S plus 1 over s plus 6. So we substitute by s minus 2. So let's do it. So minus 2 plus 1 over minus 2 plus 6. As you see, it is the minus 1 over 4. So this is our key1. Great. So let's going to the key2 factor. How we can find the key2? Key2. Let's take a look at the connected component for the key2. It is s plus 6. As you see, the root for it, it is minus 6. So let's calculating the everything for the s equal minus 6. Okay, and our fs function here will be equal everything without the components connected with the key2. S plus 1 over s plus 2. And this is equal. Let's substitute by s minus 6, and we've got how many? Minus 5 over how many? Minus 6 plus 2. It is equal how many? Minus 4. So as you see, this is equal 5 over 4. This is K2. This is K2 factor. Okay, so if we've got it, now our fs function, okay, now our fs function is given by that formula, where by the key1 and key2 we have to substitute its values which was previously calculated. Okay, so this is equal. By key1 we substitute minus 1 over 4. So it is minus 1 over 4 times 1 over s plus 2. Yeah, we've got it. Plus K2, it is 5/4 times 1/s plus 6. We've got it. And now, if we've got the Fs in such representation, we can very easy find the Ft function, which will be equal the invert Laplace transformation from Fs. And this is equal. As you see, we've got the summing of the two components, and we have to find the invert Laplace transform from each component separately. All right, so this is equal. As you see, -1/4, it is the constant value. We haven't the s here. Yeah, so this is the constant. So it is the -1/4. It is going before the invert Laplace function. And we have to calculating the invert Laplace transformation from the 1/s plus 2 plus 5/4 times invert Laplace transformation from the 1/s plus 6. So this is equal. This is equal -1/4 times. Look, maybe you'll find the invert Laplace transform from the 1/s plus 2. What function in time domain gave us the Laplace function equal 1/s plus a? Do you remember?
E2 minus a times t.
Yeah, that's right. That's right. However, a, it is 2 in our case. So the invert Laplace transform from it, it will be equal e powered to, here we've got the plus here. So it will be minus a t. A, it is 2. So it is the e powered to minus 2t. Great. Plus 5/4 times, and here, as you see, we've got the same, however, the a is different. So it is the e powered to minus 6t. Okay, so this is the result in time domain. However, we have to multiply it by unity function again. We have to remember about it. That's all. So this is the representation of the Fs function in time domain by such formula. This is a mathematical expression for it. Great. Maybe we can make another example where we will have the simple poles. Let's say we've got the Fs function equal s squared plus s plus 1 over s times s plus 1, s plus 2. Okay. So, and again, this is a simple pose example. So let's represent this, this Fs function by that form. K1, it is for the first pole, it is the s, just s plus 0, yeah, in fact, this is the s. So I put it here, the s, plus K2 for this pole, s plus 1, plus K3, it is the s plus 2. Okay, we've got it. Great. So let's calculate the Q1 again. So for Q1, we've got the roots, we've got the pole with the roots equal how many? s plus 0 means the root it is 0, yeah? Of course, when you substitute by s0, we got the 0 here. Okay, so for the s equals 0, we've got the fs function like s squared plus s plus 1 over everything without this expression with the pure s. So this is equal, how many? 0, 0, 1. And here we've got the 0 and 0. 2 times 1, it is 2. So it is 1 over 2. And this is key 1. Okay, K2. K2, the roots for K2, it is minus 1. If we substitute by s minus 1, we've got the minus 1 plus 1 is 0. So it is the s equal minus 1 here. And again, our fs function here, it is s squared plus s plus 1 over everything without expression with the s plus 1. So it is the s times s plus 2. Okay, and this is equal, we have to just substitute by s minus 1. Yeah. So it is equal minus 1 squared, this is 1, minus 1 plus 1 over minus 1 times minus 1 plus 2. And as you see, this is equal 1 over, this is the minus, this is the 1 times minus 1, it is minus 1. So as you see, this is minus 1, and this is the key 2. And the last one, K3. K3 is connected with the s plus 2 pole. So the root for it, it is s equal minus 2. And our fs function, it is s squared plus s plus 1 over s times s plus 1 without the s plus 2. And when we substitute by s minus 2, we will have how many? 4 minus 2 plus 1 over minus 2 times minus 2 plus 1. So this is equal how many? This is 3 over 2. And this is K3. Okay, we got it. Okay, so let's substitute by key 1, 2, and 3 the factors, and the fs function will be equal. Key 1, it was 1 over 2 times 1 over s. Plus, however, K2 is equal minus 1. So K2 is equal minus 1. So in fact, we have the minus here. So it will be minus 1 over s plus 1. K2 is positive, 3 over 2. So it is plus 3 over 2 times 1 over s plus 2. Great. And now we have to just find the ft function, which is equal the inverse Laplace transform from the fs function. And this is equal, okay, the first component, 1 over 2, it is the constant value times the invert Laplace transform from the 1 over s. 1 over s. How many it is? Do you remember? This is just the unity function, yeah? That's right. Yeah?
Yes.
Yeah. So we have to remember that the unity function will be on the end of our expression. So it is 1, in fact. So it is 1 over 2, just 1 over 2. Minus 1 over s plus 1. 1 over s plus 1. So this is the e powered to, here we've got the plus, so it is minus a, it is 1, so 1 I don't have to write here, and times t. It is the e to minus t. Okay, plus the constant value here, it is 3 over 2 times, and the invert Laplace transform from the 1 over s plus 2, it is e powered to, here is the plus, so we've got the minus 2 times t. And everything is multiplied by unity function. That's all. Great. So we've got the first. I think it's enough for the simple pools examples. It is not so hard, I think. Yeah. Great. So now we have to go to the next next type of the FS function, which has the multiply poles. Okay. So how are you feeling? Can we continuing, or you have enough? You are thinking that it's enough for you. Can we? Maybe yes.
Yes, so far so good.
Okay. So next example will be for the multiple pools. Okay. We've got the FS function, which is given by that formula. S plus 1 times e powered to minus 4s, for example, over s squared s plus 2. Why we got the multiple pulses here? Because we've got the s squared here, or the s to the third power to 3. Why? Because as you see here, we've got the two roots. Yeah. If you have the if we've got the squared here, as you remember from the math, yeah. If you have the function where you have the x squared plus, for example, something, it is possible to get the two roots. Yeah? That's why we can say that these examples are for the multiple pulses. Great. So how we can solve this example? First thing, it is very simple. For example, the key 0. It is the key 0. It is for the s plus 2. Yeah, the pool. Yeah, it is simple. S plus 2 as previously. Okay. Plus, and it's here we've got the s squared. So it means the s squared gave us the two pulses, and the key 1 it is for the just s, plus key 1 2 for the s squared. So now we have to find the key factors. The first one, the key 0, it is simple. Yeah, it is simple. Why? Because for the key 0, we have to take a look on the poles and find the roots. It is minus 2. For the s equal minus 2, we have to just write the fs function without this expression, this component. So this is the s plus 1 times e power to minus 4s over s squared. So if we substitute the by s minus 2, it is equal. Minus 2 plus 1, it is minus 1 times e powered to minus 2 minus 4. 4 times 2, it is 8. E power to 8 over s squared, it is 4. So it is minus e powered to 8 over 4. This is the key zero. Okay. The next one, Paul, it is also simple. Key 1, 1. As you see for this one, s, it is 0. The root is 0. Right. So the fs function will be equal s plus 1 times e to minus 4s over, without s. Yeah. However, this is the multiple poles. Yeah. So it is just the s plus 2. And how many it is? It is equal 1 times e power to 0. It is to the 0. So this is the 1 over 2, just 2. So it is just 1 over 2. And this is key 1, 1. What about this one? This is the multiple poles. So here we've got s, here we've got the s squared. Of course, the root for the s squared, it is also 0. Okay, so it is 0. However, here, if you wanted to represent, write the representation of the fs function calculating this k1, 2 factor with the pole s squared, the definition is that we have to find the derivative according to the s from the s squared times the fs function. That's the differences. Okay. So, in fact, we have to find that this representation. We have to find the derivative from such value, and then we will substitute we have to substitute by s the 0 value. Okay. So the key 1, 1 will be equal the derivative according to the s from the what? S squared times fs function, it is the s plus 1 times e power to minus 4s over s squared times s plus 2. So as you see, s squareds will be reduced, and we have to calculating the derivative from this expression. Okay, what we have it here? We've got we've got the two. In fact, we've got, let's say that we've got the two functions. In the nominator, we've got the first function, for example, f function, and here we've got the g function. And so as you see, the f, it is divided by g. If we have such case, and we have to find the derivative for that functions, like the f t over gt function, and we have to find the derivative from it. You remember that this is the ft derivative from the ft function times gt function, yeah, minus ft times derivative from the gt function over gt squared. That's right? Yeah, you agree with me or not?
Yes.
Yes. Okay, but you have to be very careful, because in nominator, in fact, we've got of course, the ft function is here. However, it consists with two functions, s plus 1 times e power to minus 4s. So if you wanted to find the derivative from the ft function, which is in fact the multiplication of two functions, in fact we have to use that formula, in fact, for only ft functions, derivative from the ft functions. Okay, how it looks like. It is equal, step by step. It is the ft function prim, so it is the s plus 1 e to minus 4s prim times gt. It is the s plus 2 minus our function ft function. It is the s plus 1 e power to minus 4s times here derivative from the gt function in of course gs function, of course, but the gt in fact, or gs here, it is the s plus 2. What is the derivative according to the s from the s plus 2? Do you know? What is the derivative according to the s from the expression like the s plus 2? How many?
1.
Of course, 1. Yeah, of course, because we've got the constant value equal 1 before the s. So this is the constant. So the derivative from it, it is just the 1. Yeah, of course. Over by the gt squared function. In fact, gt for us, it is s plus 2. So it is the s plus 2 squared. All right. So this is equal. Everything we've got. However, we have to find the derivative from this function, which is consists with the two function which is multiplied. So we have to, how we can make it in the same way. However, we have to forget about it. And if we got the two functions which is the which is multiplied, and we wanted to find the derivative from it, we use that formula for it. Yeah. So as you see, for the first function in the bracket here, it is s plus 1. So derivative from it, it is equal 1. Okay, so it is 1 times the second function, e minus 4s. 1 times e minus 4s minus, minus, and here we've got the s plus 1.
I'm sorry.
Yeah.
The product rule isn't with a plus inside?
Well,
because the quotient rule is f prime gt minus f t gt prime, and the product rule is not the same. It's plus instead of minus.
Here is a plus?
I think so.
No. No.
No, it's minus.
It's minus.
That's the quotient.
Yes, but for the quotient, but for the product rule inside the brackets, the first
Here?
one. No, on the left, the s plus 1 e to minus 4s.
S plus 1 e to.
Yes, and when we are calculating it, it's a product rule, yes?
Yeah, this is our function here. In fact, that's right.
Yes.
Yes, which is consists of two functions in s plus 1 times e power to minus 4s. And
Yes.
if you wanted to find the derivative from only from this expression, which is consists by two functions, we used the same, as I remember, expression with minus here or not. Then it is plus. I will check it.
Yes, plus.
I'm talking about the product
Yeah.
rule. I know about the quotient, but then after using the quotient rule, we have to use a product rule for calculating the product of derivative of s plus 1 this is in the bracket, times e minus 4s. These are two functions. And
Yeah.
to calculate this derivative, we need to use the product rule, which uses plus inside.
A plus inside, yeah?
Yeah, and it will be just
Okay,
f.
okay,
Yes.
okay, Grzegorz. Maybe you have right. Maybe I make some mistake. It is possible.
The catch is that derivative of e will give us minus, so shouldn't matter at the end.
Where it is? Oh, it is here. Here it is. Okay, and the properties of the functions. Yes. You have right. You have right. We've got the plus there. Grzegorz, you have right. So here we've got the plus. Yeah, Grzegorz, that's right.
I didn't calculate it yet, but I was talking about the general formula.
General formula, yeah. So if you've got the two functions, ft times gt, and we wanted to find
Yes.
derivative from it, it is the ft prim times gt plus ft times gt prim.
Yes, because I've heard you saying the minus, and I
Yeah,
wanted
that's
to
right.
correct it. Yes,
Yeah,
thanks.
of course. Yeah, you have right. Thank you for it. That's why, in fact, we've got the ft prim function from the s plus 1. It is 1 times e minus 4s. So this is it. Plus, and the ft function in our case is s plus 1 times the derivative from the second one. Derivative from the e, yeah, it is how many? E powered to minus 4s. However, the internal derivative from here, it is minus 4.
Four.
Yeah, that's right. Yeah.
Yes.
Yeah, so that's why here, in fact, we'll have the plus, but we'll have the minus. Yeah. Yeah, because the 4, it is minus 4, in fact. Yeah. And everything is multiplied by s plus 2. But general, of course, Grzegorz, you had right. Yeah. Minus s plus 1 e power to minus 4s over s plus 2 squared. Yeah. Okay, so this is equal. And we have to multiply everything by the s plus 2. So it is equal e to minus 4s times s plus 2 minus s plus 1 times s plus 2 times 4e to minus 4s. Okay. Okay, minus s plus 1 e to minus 4s over s plus 2 squared, and everything we have to calculating for the s equals 0, as we remember. Okay, so let's find the result here. Here it is 1. From this it is 1. S plus 2, it is 2. Here we've got the 1. Here we've got the 2. This e to minus 4 to 0, it is 1. So it is 4. And here it is the 1. And this is the 1. All right. So as you see, I've got the 1 times 2, it is 2. Minus 1 times 2, it is 2 times 4, it is 8. Times 1, it is 8, okay. Minus 1 times 1, it is 1. Over the 2 squared, it is 4. Yeah. That's right. Okay. This is minus, this is minus. Okay, yeah, that's right. So how many it is?
-7/4.
Yeah. And this is our key 1-2 factor. Okay, so now let's coming back to our example and expression for the Fs in that formula. So let's substitute by the factors everything what we calculating. Great. So the Fs will be equal K0. It was -e⁴ times 1/s+2 plus Q11. It is equal Q11 1/2. So 1/2 times 1/s. Okay, and the last one, it is -7/4. So it is not plus but -7/4 times s squared. 1/s². So so as you see, this is our Fs function, and let's finding the Ft function, which is equal to the invert from the Fs. So this is equal. Okay, we've got the three components, the sum of the three components. The first one, the constant value, it is -e⁴ e⁴ Yeah, this is the constant value times 1/s+2. The Laplace, the inverse Laplace transform from it. It is how many? E
to the -2t.
Great, excellent, Dominique. Great. Plus the constant, it is 1/2 times the inverse Laplace from the 1/s. It is
The unity function.
1.
Yeah, the unity function. That's right. So it is 1 here. This unity will be at the end of our expression. Great. Minus 7/4. It is just the constant, and the inverse Laplace transform from the 1/s². This is the
T.
Great. This is the t, and everything it is multiplied by unity function. That's all. Yeah, this is the example for the multiple pulses. Great. Whoa. And last one, the last example will be for the complex conjugate pulses, but I don't think so that we have enough time. Yeah, because today we've got it 2 hours only. So I think we'll continue it in the next classes. Yeah, in the next week, and we'll finish the examples with the conjugate pulses, and then we'll starting with the calculating of the Laplace transform based electronic circuits. All right.
Okay.
Sir.
All right. So thank you for watching this today courses, and what else we'll see in the next week. That's right, on Tuesday.
Excuse me, sir.
Yeah, Barry? Yes? Yeah? Hello? Barry? Do you hear me?
I would like to ask something, but
Yes.
I will send you an email.
Yeah, you can ask me, yeah.
I will send you an email.
You send me an email, yeah?
Yes.
Okay. I'm going to reading, and I will ask you. I will write the answer. Okay.
Okay. Thank you.
Okay. So thank you again. So we'll see in the next week. Yeah. Okay. Do you have any question? The rest of this. Do you have any question?
No, sir. Thank you for the lesson.
Okay. Thank you. See you. Bye.